Hello and welcome to Gardeners of the Galaxy, the podcast for all of the sentient beings in the universe who have a passion for plants. I am Emma the Space Gardener and I will be your host as we explore gardening on Earth and beyond. In January this year, thousands of people were entranced by the flowering of a plant nicknamed Putrescia at the Sydney Royal Botanic Gardens. Putrescia is a Titanarum, an example of an endangered plant also known as the corpse flower because of its putrid stink. Once every few years, the Titanarum produces a single, impressively large flower that lasts just 24 hours. The plant is native to Sumatra, and the first time it bloomed anywhere else was in 1889 in Kew Gardens from seeds collected by Italian botanist Edoardo Beccari in 1878. The second time it flowered, in 1926, it caused such a sensation that police were needed to keep the large crowds in order. It's such a rare event that over the following century, Titanarums only bloomed in botanic gardens 21 times. Now, of course, the internet means that enthusiasts can watch the flowering process online, although since we have yet to invent smell-o-vision, it's not quite the same experience. I haven't yet been present for the flowering of a Titanarum. I have, however, witnessed an entirely different periodic event, the arrival of a visible comet in Earth's skies. I vaguely remember the last visit of Halley's Comet to our little patch of the solar system in 1986. There have been more recent comets, of course, but I live in an extremely cloudy part of the planet, so I usually miss out on seeing them. It doesn't seem like there's much of a connection between these two natural phenomena, the flowering of a Titanarum and the orbit of a comet, and yet there is. That's because the Titanarum is one of a surprising number of plants that can produce sizable amounts of heat. In the case of Putrescia, it's a tactic to encourage the spread of its putrid smell and make the flower appear more like rotting meat. That attracts the kind of insects who like to lay their eggs in rotting meat, providing a plentiful supply of pollinators. I can't imagine people queuing to see a skunk cabbage flowering. This much more commonplace event takes place on the banks of streams and in swamps. The plant produces a purplish hood known as a spathe, which surrounds multiple small flowers on a central spadix. But thanks to the energy stored in its rhizome, the skunk cabbage can maintain a high temperature inside the spathe, even when it's freezing outside, for nearly 2 weeks. It prevents the build-up of snow and ice on and around the spathe, but it's not 100% clear why the plant bothers. Its strategy may be to lure in early pollinators when there's very little else around for them. Plants that produce heat like this are called thermogenic, but what has any of this got to do with comets? This is where a theoretical physicist and mathematician called Freeman Dyson enters our story. In November 1997, when the search for life beyond Earth was at a considerably earlier stage than it is now, The Atlantic published an article by Freeman Dyson in which he theorised that warm-blooded plants, as he called them, could exist on Mars. His reasoning was that any life form that survived from the early warm and wet era of the planet to the present cold and dry one would have adopted one of two strategies. He considered the first, retreating to living underground where liquid water could still be found, to be the most likely, although very difficult to detect. The second was that an organism could have remained on the surface but evolved a protective shell, an insulating greenhouse, in which it could remain warm and moist. He was wondering, in short, whether thermogenic plants could have evolved to tolerate the conditions on modern Mars. He theorised that plants could grow greenhouses in the same way that turtles grow shells, a thick skin to provide thermal insulation, with transparent windows to let in light for photosynthesis. He doesn't mention it, but to me it brings to mind lithops, the living stones that have leaf windows that channel light to interior leaves. On Mars, the windows would have to be small to minimise heat loss, he said, and the plant would need deep roots to tap into water and nutrients from warmer underground layers. The plant's greenhouse would create an environment in which oxygen could persist and perhaps support aerobic microbes and animals. Groups of plants could create extended habitats for other plants and animals, and fungi and microbes could form symbiotic relationships to help the plants extract nutrients from ice or soil, as they do on Earth. Dyson knew that finding these warm-blooded plants on Mars or anywhere else was unlikely. But he also theorised that one day they could be a tool allowing humans to colonise the solar system, in particular the millions of comets in the Kuiper Belt. Dyson thought that it would take 100 years or so for us to develop the biotechnology to grow warm-blooded plants. He said that their seeds would be the most useful ones for future space colonists to pack in their luggage. He envisioned tree-sized plants growing greenhouses large enough for humans to inhabit, planted by robotic missions, and full-sized by the time explorers arrived. For Freeman Dyson, the galaxy was a beautiful place, but a bit boring if it wasn't alive compared to our planet that is teeming with life. He wanted to bring life to the universe and bring the universe to life, a concept he called greening the galaxy. He foresaw one day growing potatoes on Mars, but he also saw the potential lurking in the Kuiper Belt, where possibly trillions of comets provide far more real estate than all the planets combined. When life spread out from planet Earth, he reasoned, this is where it would have to go. Asteroids are rocky, but comets are cosmic snowballs, dirty chunks of ice with all of the common elements necessary for life. They also have a slower orbital speed, and although the Kuiper Belt may currently seem cold and uninhabitable, Dyson thought it may be less inhospitable to life than Mars. Living there would be similar to life on an archipelago, he thought. Communication and travel between the small ice islands would be easy, he said. It would only take a few days' travel in a spaceship to hop across to a nearby comet to visit neighbours or purchase supplies. You could even capture and tether a passing comet to add to your little empire, gradually building up quite a metropolis. Comets have very low gravity, so there would be no limit on the height of our bioengineered trees, which could grow to be hundreds of miles high, spreading out from the comet in all directions to collect enough sunlight. Seeded onto a comet, a mature Dyson tree could generate enough heat and oxygen to support an ecosystem inside the comet. From the outside, the comet would look like a gigantic leafy spaceship, half natural and half engineered. A Dyson tree growing from a comet the size of Manhattan could support millions of people. And Dyson looked ahead to a time when we'll be able to design entire biospheres tailored for the environments on different planets, moons, asteroids and comets. We would design an egg weighing several kilos out of which the entire biosphere could grow. Each egg would be a miniature Noah's Ark crammed with millions of microscopic eggs programmed to grow into the different species and the nutrients and life support needed to kickstart their growth. The first species to emerge would be warm-blooded plants designed to provide warmth and shelter for other organisms. We could send out small spacecraft with eggs to seed a great abundance and variety of life in all kinds of places. Not all of the biospheres would survive, and those that did would evolve in ways we could never imagine, with or without a human presence. We could bring life to the universe, he thought, as far from Earth as our biosphere eggs could travel. For now, Dyson trees remain very much in the science fiction realm. Perhaps one day we really will be ready to send the seeds of thermogenic plants out into the solar system to grow homes for future generations. And if that time comes, let's hope our genetic engineering efforts have managed to remove the funky smell. You can find the show notes for this episode with links to the Atlantic article and other interesting things on my website, spacebotany.uk. And don't forget that you can sign up to the weekly Gardens of the Galaxy newsletter for more astrobotany content. That's it for this episode, so I'll hand you back to Mission Control. Capcom, speaking of warm things, have I got time for a nice cup of tea?
Orbital Gardens, this is Mission Control, confirming termination of your signal. We have activated the auto kettle and you are T minus 3 minutes. Mission Control out.